that. Yeah, don't need to chat.
Yeah.
Side.
Take a little bit more time. Yeah, now one
Outside view. I think that's probably best we can do. And switch the video on if you want to.
I think it's okay as it is.
Switch the video on to get a little. Okay. I think we're good to go. Adam, are we okay? Yeah. All right.
Thank you, Ray. Okay, thank you everybody for your patience. So I'm very pleased to be able to introduce today our keynote speaker, Ghica, who is a professor of programming language semantics in the University of Birmingham, and also the director of Programming Languages Research Lab in Edinburgh, Huawei, Edinburgh. So Dan has been working in the topics that we are all interested in research, and he has done very interesting work on several different aspects of graphs, graph transformation, computational models, from very deep theoretical results on game semantics to very applied work on building industrial strength compilers for programming languages based on those ideas. So the whole spectrum, using obviously graphs and graph transformations in various forms, different kinds of graphs, different kinds of graph-based models. And very recently, as I said, this very interesting work with applying graph transformation techniques to build compilers. And one of the important issues there is representation of programming language syntax. So Dan is going to tell us today about these very interesting ideas of using diagrammatic representations. And I'm going to stop here because it's so very interesting and to control here. Thank you, Dan.
Okay. Thank you. Thank you for inviting me. It's quite an honor to be here, especially since I'm not really, I wouldn't consider myself in the mainstream of graph theory or graph transformation, but I think once in a while conferences decide to invite people peripheral to the subject area, maybe to show or to showcase the potential for interaction. And as Maribel said, my work has been quite interdisciplinary. My true background is in programming language, semantics, and related aspects such as type systems and programming logics. And as such, most of my, let's say, my formative education in programming languages is in a term-based environment. But more and more, working with representation, with concrete representation, syntax, I came to have my own conversion, to keep in the spirit of the theme that I'm proposing here, to see the benefits and the advantages of graph-based representation. And I have also tried to communicate these ideas to people who work in the mainstream of programming languages to understand the benefits of graph-based representation and orienting the study of programming languages indeed on a graph-based rather than a term-based set, which has, as I hope to illustrate over the next hour or so, with particular advantages. So just to give a very quick introduction, lambda calculus is obviously a term-based calculus, and the mainstream study of lambda calculus is in a term-based setting. But that didn't stop people looking at graphical and graph-based formulations of the lambda calculus throughout the years. Some of them quite whimsical, some of them quite theoretically interesting, some of them formal, some of them informal, some of them purely pen and paper, some of them fully fledged tools. And also people tried programming languages with a visual graph-based syntax along the same lines, because there is something intuitive and appealing, just kind of right off the bat. And when people see pictures, sometimes they find them more appealing than when they see sequences of symbols, particularly some of them are from the Greek alphabet, which is many newcomers find intimidating. The pictures are a good introductory way to build intuitions among many other advantages. But the question is, what is the correct graphical syntax of the lambda calculus? And to go a bit further, what is the correct graphical syntax for functional programming? Can we develop such a syntax in a principled way, or do we have to reach for some kind of core ad hoc intuitions and build on top of them? And what I want to propose in this talk is that the thesis that we can construct such a graphical syntax in a principled way so that it has not only, hopefully, visual appeal, but also good theoretical properties. A lot of what I'm going to talk today is based on this preprint, which summarizes. It's quite recent. Published it on the archive in the last couple of months, and it summarizes my work on string diagrams together with Fabio Zanazzi. And also, you can think of this talk as an extended pitch for you to reach out and read this paper. The talk is going to be much more superficial than the paper. The paper is more than 100 pages long. It is an advanced technical introduction, tutorial introduction, which should be accessible to people without any specific backgrounds, and also without sacrificing technical precision. So let's start with this kind of basic question of what is syntax. Here on the left, you see term-based syntax of a lambda term. And there on the right, you see a naive abstract syntax tree of that same term. And there are obviously two very different representations of the same concept. The concept itself is an abstract concept, but it has, as any abstract concept does, many possible representations. So I want to dissect this difference between the term-based and here's an abstract syntax tree. We can already call it a graph-based representation of syntax. Why do we have these two representations? And initially, the representation is one that is completely pragmatic. We are people, and as people, we are very used to reading and writing, and the large majority of our reading and writing experience is based on linear languages, which are sequences of symbols, and that is the term-based syntax. It's a syntax that arises naturally out of the need for human consumption. On the other hand, we also need to write tools to process these languages, compilers, interpreters, static analysis, all sorts of tools that they need to process syntax. And that's very quickly when you start from the very beginning, historical beginnings of the area of compilers. We realized that working directly on text is incredibly inefficient. You don't want to write tools that operate on text. You need a better representation, and the abstract syntax tree is the original graph-based representation of syntax intended for algorithmic consumption. It's called abstract syntax tree. It's not very abstract at all. It's actually very concrete, but as opposed to text, it elides certain detail. When you build the abstract syntax tree, for example, you don't need to represent the parentheses, and that's just small detail, which obviously, especially in the Lambda calculus, you're going to see a lot of parentheses, but the abstract syntax tree, those parentheses disappear. And that was enough to get people excited and call them abstract because, hey, no parentheses. But it's a distinction that actually is interesting because as we shall see, as we move from terms to graphs, the representation becomes more and more abstract in the sense that more and more detail can be elided without loss of precision. I also don't think that moving to a graph-based formalism is going to remove the need for term-based formalism. The term-based and the graph-based formalism, they have to live together. The term-based is tried and tested for both for reading and for writing code, and it also scales up incredibly well. I don't know if you ever tried to read through a code base of thousands of lines of code. It's doable. I'll try to go through a graph with thousands of nodes. It gets a little bit more difficult. So these two things have to coexist, and they are related. Like we can always go from the term to the graph using something that we all know as parsing, but also we can go from the graph back to the term using some form of serialization of the graph. And if these two are connected together, they're going to form some kind of a junction in the sense that if we start from a graph, we're going to get back to the same graph. But if we start from the term, we're going to get back to some kind of normal form of the term, which informally is called pretty. So now, since we're talking about, I made this point about the fact that I want to talk about good syntax. So this abstract syntax tree, in some sense, is better than the term because it elides some detail of representation, namely the parentheses. What is a good syntax? So let's look at some examples of terms, and that's what I say. If we take some kind of language where we have leg bindings. Here you have the text without a brackets, and here we have text, the same term, but with brackets inserted. And obviously, these two are syntactically equal, but they are syntactically equal in the AST. They're not syntactically equal on the concrete syntax because obviously, if you compare them as strings, they're not going to be equal as strings. So that's why the AST is more abstract, so better than the term because it omits detail. But there are many other such equivalencies at the level of syntax. Probably the most important one is alpha equivalence. We can systematically rename bound variables in a term. So these two terms are equivalent because I have systematically renamed variable y as u. And they're not equal as terms. They're not equal as abstract syntax trees, but there are techniques of representation, namely based on nominal techniques as developed by, probably most prominently by Andy Pitts in Cambridge, to give to give representations, concrete representations that absorb alpha equivalents. There are other well-known concrete representations that absorb alpha equivalents, such as the Brown indices. And in that sense, again, they are, from that point of view, you can think of them as better syntax. But there's more. Notice that the definition of X and the definition of Y do not share any variable, therefore, we can swap them. And this is something that the term and the AST are not gonna be equal as term. They're not going to be equal as AST. They're not going to be equal modulo alpha equivalence either. And these equivalents, this is a congruence that's very important in calculi of explicit substitution. So if you think about this let here as if you interpret it as an explicit substitution, then in modern calculi of explicit substitution, terms are interpreted modulo this congruence, which is called graph equivalence. Why? Because if you build this, as we shall see, as graphs, they are actually going to give you isomorphic graphs. So graphs are going to capture that notion of equivalence. They're going to absorb it into the natural notion of equivalence, which is graph equivalence. But it's not reflected by terms or by ASTs. And finally, we can have equivalences that given by the fact that certain operations are, for example, associative or commutative. And this again is not reflected in the syntax, but at the level of graphs, it can be made. It can be absorbed. So it is possible to make this term and this term have the same graph representation. So that is these are kind of the rules of the game, that the more terms that in the term syntax, you have to explicitly quotient by some congruence. On the other hand, in some other syntax, which is going to be obviously the graph syntax, they become equal, which means graph isomorphic. Then the better your representation is, the better your syntax is. Now, how do we get from terms to graphs? As I said, they have the terms and the graphs. They need to coexist because they have different qualities that recommend them. We need to bridge this gap somehow. We don't want to resort to raw intuition. We don't want to come up with ad hoc definitions because that's tricky. You can always get things wrong. But it turns out that factoring these trajectory from terms to graphs through categorical syntax, it gives us the right. In the end, it will give us the right graph syntax. And the reason is, and the thing that was kind of very eye-opening to a lot of people working on categorical syntax in the early 2000s, is that there is a way to write the syntax of terms in category theory in a graphical way. And now here I'm going to use two words, graph and graphical. Graphical, I just mean something that looks diagrammatic, but without being defined as a formal combinatorial object. And by graph, I mean a formal combinatorial object. But the graphical rendering of string diagrams takes us in a very obvious way to the world of graphs as combinatorial objects that we can work with formally and algorithm. And that's basically this trajectory, this methodology is what I'm going to illustrate in this talk. And yeah, and I call it a syntactic trinity because as I have noticed in my work, where in an industrial laboratory where we are actually implementing compilers, is that all these three things are essential and they need to coexist. The terms are the basic representation that is accessible to humans. The graphs are the essential representation that is useful for computers, and the categorical syntax is the essential representation if you want to write proofs in a way that is tractable. At this level and at that level, the proofs are very difficult. At the categorical level, the proofs are much more appealing. But the algorithmic properties of the categorical syntax are completely terrible. So we cannot discard any of the members. Okay. What do I mean by two-dimensional syntax? Is just, for example, I mean the simplest intuition that I can appeal, like an experience that you should have, is the representation of matrices. We think of matrices, like when we teach matrices in school to students, we teach them as two-dimensional objects. But if you want to formalize it, you have to think of it either as a row of equal lengths or as a column of equal length rows. And that is a lot harder because you see, if you want to prove something such as the fact that the transposition of a matrix is involutive, if you appeal to this two-dimensional representation, it's extremely easy to explain it and to teach it to a student. Whereas if you want properly formalized, like flattening the 2D representation into some 1D representation that a proof assistant such as Agda would accept, then you end up with a lot more work because the change of representation induces a lot of encodings, and then your proof have to be at the level of the encodings, not at the level of the original intended representation, which, by the way, I don't think we know how to formalize it quite yet. I haven't seen any good studies of two-dimensional syntax as opposed to one-dimensional syntax, where again, the right notions of equivalence are packaged into the syntax itself. So one-dimensional syntax, in one-dimensional syntax, there's pretty much only one thing that we can do, is that we can get rid of the brackets if we have an associative operator. So if I have these kind of operation, which let's write it as semicolon, which is associative, then any bracketing on the left would do. So we can get rid of it, and that means that all these terms are going to be equal, and they can be given a canonical representation, which is some kind of a fixed or default or implicit bracketing that we put on the right-hand side, so that if we only have the associative operators, we can get rid of the brackets. But that is quite limited. That's the only thing that we can do on the one-dimensional representation. We can do a lot more in the two-dimensional, and then even more, as we shall see, on the graph. So the two-dimensional syntax, which goes back to papers by Joel and Street on something that's called monoidal categories. So these are, for those of you, now that is a bit difficult to present because some of you obviously know category theory. So what I'm going to say is trivial, and some of you don't know category theory. And then maybe what I'm going to say is going to be opaque. So I'm going to target my explanation naively to people who don't know category theory. And I hope people who know category theory will indulge me because there's going to be some oversimplifications for the sake of telling a better story. So please don't correct me. So monoidal categories is an algebra where we have two kinds of compositions, one that we call sequential composition and one that we call vertical composition or monoidal tensor. And the terms, we're going to write it as boxes, and the types of the terms we're going to write as wires. And if we compose two terms, F semicolon G, we put them next to each other. And because these two guys have the same type on the left and on the right, the composition has to be well typed, then we do some kind of calligraphy. Think of it right now as an artifact of calligraphy, like joined up writing. When you write the letters and you connect them to each other, they're still discrete. So the best way to think of this is there's tiles in a plane, but because they have the same type, we're going to connect. And because we're going to connect them like that, that is obviously also because eventually these guys will become graphs. And we have an identity which is written just like a wire. So we have an algebra of boxes and wires that can be connected in a way that doesn't break the types of the wires. In the one-dimensional syntax, we have brackets to identify subterms of interest. In the two-dimensional syntax, we have boxes
to identify sub-diagrams of interest. And this is an idea that goes to Andre Méliès. It's also not that far back. And if these boxes, we annotate it with a label, we can think of them as maps. Maps that act on the boxes and maps that act on the wires separately, in a nice way so that they don't break the typing. So if F acts on F, is going to give the types FA and FB when it acts on the wire. So it's coherent, it doesn't break the typing. Moreover, if these boxes have the following two extra coherences, then they represent something that's called functors in category theory. So if we act on the identity, we get the identity, and if we act on composition, we get a composition. So this box, this functorial box, distributes neatly across all my compositions. And now that gives us quite a lot of expressiveness, so we can write equations in category theory, which are quite nice. Already expressing things that are quite complicated to express one-dimensionally, two-dimensionally. So, for example, the concept of a natural transformation, which are families of. So here, the natural transformation is families of type-indexed boxes that have the property that they commute in a certain way with two functors f and g, case in which we say that the natural transformation is between f and g. And the equations here, I rendered them directly diagrammatically, which you can simplify them further if you want to by incorporating these textual labels into graphical convention and by inferring all the data that can be inferred rather than spelling it out explicitly. And this kind of makes it quite intuitive what the main coherence rule of natural transformation is, some kind of commutativity through the two functors. And two natural transformations are called functors if they satisfy, they're called a junction if they satisfy two extra, they're natural transformation that satisfy two extra cancellative rules between is called epsilon and eta, the unit and the co-unit of the adjunction. So again, we can write it diagrammatically. We can use color conventions, and we can make things neat and pretty, and without sacrificing actually formality. From something like this that looks pretty because it doesn't have a lot of redundant information, we can infer everything that we need just from the color coding and the annotations, few as they are. And then once we get it to this form, we can completely recover the term formulation of the original term formulation of the equation. So right now we don't have, we're not buying anything extra a lot other than prettiness. But that is still nice. I think that can still be a nice and fairly accessible introduction to quite advanced things in category theory, such as adjunction, because there are two presentations of adjunctions. One is in terms of these kind of equational properties of the unit and the co-unit. The other one is by showing that all the boxing between FA and V, the set of boxes between FA and V is isomorphic to the set of boxes between A and GB. And if we define it in one way, it has to satisfy the other definition, and we can do the proof in a graphical way, which is quite neat and unintimidating. And again, I only recommend you as an exercise to look at these kind of graphical proof, which again, I emphasize, this is a proof. This is not a picture to guide intuition. It's an actual graphical proof. and compare it to the term-based proof. And I think we'll find that this one is not just looks simple, but the intuitions of what's going on are much better captured. Probably you have noticed that we haven't gone 2D yet. These are still boxes and wires, but they were kind of 1D. Two-dimensional is when we introduce, if they become truly two-dimensional, when we introduce the monoidal tensor, which is the vertical composition or the stacking of my boxes. And in category theory, the monoidal tensor is associative up to isomorphism. So if I stack A on top of B and on top of C in the two different possible ways, I get isomorphic objects. If I get actually equal objects, then that is called a strict monoidal tensor. And because this guy now is equal to this guy, just like in the case of the sequential parentheses that we can remove in the case of associativity, here we have these boxes are vertical parentheses. We have a kind of associativity on the nose, so we can remove them and we can just write things like this, and which truly gets us into the realm of two-dimensional syntax. And also the unit of the tensor, again, because it's an identity up to equality, not up to isomorphism, we can implement it, we can represent it by a graphical convention just as empty space, because stacking empty space on top or on the bottom of a box, it gives us back to the same box. So in this case, the graphical convention truly captures the equation, the coherence that we want. So we can write an expression now in our two-dimensional syntax. So we have the tensor to put in boxes, to stack boxes, and we have sequential composition to connect things like this. And we also introduce some constants now: the box for true, the box for false, and some boxes for logical operators. And now this looks like an abstract syntax tree, but written in a weird way. And this way of writing it is not just weird, but it's also incredibly inconvenient, because how am I gonna? Where is this radix? T, if I want to calculate T, F, or, well, it's gonna be T is here, F is hooked, T, F, and or is all the way here, right? Because I took my abstract syntax, what we think of an abstract syntax tree, and I just put it on the grid. When I put it on the grid, then the connections become unclear. So that's the term form. But in the diagram form, I can actually spot these radixes, and I spot them because now I can think, this is actually a graph. And as a graph, these guys are subgraphs without being subterms. And that's a really powerful thing about the graphs, is that subgraphs are much more expressive than subterms. So they allow you to find radixes in a way that, in order to find them in a term, you would have to use a lot of commutativity, associativity, distribution laws, which are not directional, and they give you a huge search space. So they're not good. So one of the kind of typical examples of using this representation is that if I distribute the sequential over the stacking of the boxes, then I get the same thing. So this diagram can be represented either like this or like that as a term, and they give me exactly the same two-dimensional diagram. And that's, I would say, it's a sign that we have not just a good but a great syntax. This is very difficult to work with because there's a lot of distributivity and associativity going on, whereas here you just have the same. Now, in order to get from the string diagrams that, by the way, there's a big literature on string diagrams in all sorts of areas. I'm not going to talk about that because especially coming from the world of quantum systems. There's a lot of work on quantum system. And in fact, I was a postdoc at the time in Oxford at the time when Bob Cook and Samson Bramsky had the great push for using diagrammatics in quantum communication, in quantum computing, and I was obviously very influenced by that. There is one problem when you want to use string diagrams for programming languages, is that in programming languages, the monoidal tensor is not string. We use monoidal tensor to represent things like sums and products in programming languages. And obviously in a programming language, product is not associative up to equality, but up to isomorphism. So there's some bureaucracy that we need to do in order to get these non-strict monoidal tensor correctly. And this was a paper that was quite recent, done with mainly by Paul Wilson, who was Fabio Zanassi's PhD student. And it turns out that it's actually doing something that everybody thinks is boring and trying to spell out the technical details can be actually quite interesting and rewarding. So now we have these constructors that allow us to basically group wires with individual labels into wires with composite labels. So now if I want to construct this on the left and this on the right, on the left I get this, on the right I get this, but these guys here in the middle, these strictification and destrictification, putting two wires together and splitting them, are going to cancel out. So this diagram is going to simplify into this diagram, which is then going to be equal. And that also gives us a very nice diagrammatic perspective on a very important theorem of Maclane's in category theory, the coherence theorem for monoidal categories. And the diagrammatic perspective basically says that these guys, when we work in a non-strict category, all these strictifiers and destrictifiers occurring internally are always going to cancel each other out. So in the end, we're going to end up with essentially the same diagram as in a strict monoidal category, so without strictifiers and destrictifiers, but they're going to have a tree of strictifiers and destrictifiers associating in particular ways the interface of the box. And that I find that very neat, because this theorem is often, people try to explain it informally, because it seems to have some very obvious intuitions that are buried into a lot of technical stuff. And I think this diagrammatic perspective gives you that. We can also use it to formalize certain things nicer, having these strictifiers and destrictifier, and it also allows us to overload some graphical conventions without losing precision and without becoming imprecise. So you can tell probably I'm quite fond of this stuff. We can do more. We can add other operations from category theory, such as symmetry, the fact that we can swap two wires and then swap them back again, and then they cancel each other out. And they have a bunch of equational properties that justify a particular graphical representation of representing the symmetry as just two intersecting wires. And then we can, with what we have so far, we can build the apparatus of a symmetric monoidal category. We saw category in which we can also swap boxes in a completely diagrammatic and rigorous way. And up to that point, except for the strict versus non-strict business, we are entirely in the same world in which things such as quantum computation happen. Moving to the world of programming languages, now we need to deal with the structures for abstraction and application. And that's called the closed monoidal structure. So the closed monoidal structure is something that can be defined in terms of adjunction, which I presented a bit earlier. So basically, without going through all the details, we're gonna say that this gadget here, which represents which we can create out of a junction that is presumed that it exists. So we have the functor on the left of the junction, which is tensoring with some wire. So I didn't write that down, but basically the functor is this one. So it's just basically having a box and drawing an X wire underneath it. That is this functor. And we have to postulate, we have to say that it has an adjoint, and we give a definition of that adjoint as being constructed of this, which we give it as the syntactic sugar, but the syntactic sugar of the graphical notation of this. So here you have the box that represents to the term. A here represents to the free variables of term. X represents the bound variables of the term, which are connected to the box to indicate the fact that they are bound. And they need to satisfy certain equations, which we can check that indeed with this definition, these equations are satisfied. This can be checked graphically, of course. Everything can be done graphically, and we can be happy. And then we can prove, for example, that other definitions that we expect to hold for this algebraic structure that's needed to model higher order functions can also be proven correct. So this is a definition that basically represents the currying and uncurrying isomorphism. So if I have a function with two arguments, it's the same thing as having two functions defined like this. And that can be proved graphically, rigorously in this setting. So that's nice. And we can get another definition, and this is the definition that comes closest to syntax, which says that I can generate any two-dimensional diagram out of abstraction and application, modulo these three equations, and that also is going to be a valid symmetric monoidal closed category. So it's going to be a valid representation for higher order functions and applications. And here we notice that obviously not all equations of a theory will be absorbed in the graphical syntax. So here we have actual computation happening, such as the beta law, the fact that we are applying a function to an abstraction, and then the function and the abstraction cancel away. And so these are computations. These are not rules that can be. It's not a mathematical statement. This is just kind of a. If you can come up with a syntax that can make these rules implicit, absorb into the syntax, of course, they can be done, but intuitively, this should not be possible because these are all rules that have something to do with computation. And in some sense now, we can say that we have reached our objective. We do have a syntax for the lambda calculus. We do have a syntax for programming languages because we have already shown that it satisfies all the correct mathematical properties to serve as a model for the lambda. All right. So here again, the proofs that what I said before is true. Again, they can be performed rigorously and diagrammatically to show that indeed this freely generated symmetric monoidal closed category is a monoidal closed category. So it's not just something that we call it; it is that. One more thing that we need to get right is copying, and discarding, which is Cartesian product. And the Cartesian product, which means at the level of term, it means that variables can be introduced and then used multiple times or no times at all. And diagrammatically, this is represented by a copying node and a discarding node. So if think of these edges as variables, if this variable is bound to F and it's used twice, it's the same thing as inlining F. So copying it twice and then sharing, pushing the sharing to whatever variables the two instances of F have in common now. And obviously, if a variable F is bound but not used, we can just drop it. And this dot here with the copying, and this dot here with the reason why I'm using the same dot for both is that, in fact, if you create any kind of tree-like structure out of these two dots, it can be brought to a normal form, and then it can be just represented as an n-ary dot, where n can be anything from 0 to some finite value. So again, any representation like this can be simplified to that, and that without losing anything in terms of correctness of this. So let's see how we can interpret the simplified lambda calculus in this graphical notation. And here it was kind of something like, just like in the case of the strictification stuff, it was a simple, like a tiny pet peeve of mine, is that if you go to standard textbooks on graphical model, also categorical models of the simplified lambda calculus, you're going to get some interpretations like this. But they capture a bit of a lie here. So for example, here, see, this is the environment where I have my free variables and I'm extracting a variable out of it. So obviously I'm going to have the projection. So its projection is a tensor of the identity with discard. And that seems all nice and dandy, except that how did this variable end up at the top of my environment? The variable could be buried somewhere inside the environment. The same thing in the case of abstraction. If the variable has to be at the top of the environment, it's nice and dandy. But what happens if the variable is not at the top of the environment? Then you have to do a lot of these boring things that have to do with the fact that your tensor is non-strict. You have to associate things. You have to, using algebra, you have to push it to the front of your environment and then get rid of it. So if you want to spell it out correctly, these rules with all the associations needed, it's a lot of work, and it's unpleasant, and you can understand why people don't put these things in the papers, because category theory is unappealing enough to many as it is. We don't want to make it any harder. But now, if we use the diagrammatic representation, all this bureaucracy here is a bunch of strictifiers and districtifiers, which we know from Maclane's coherence theorem that they will cancel out always, which they do. So all these guys here cancel out, and you indeed end up with that at the top. So now you can have elegant, simple equational interpretation of the lambda calculus without lying, and that's good. I think that's great. I'm very happy with that.
Maybe a question here. So you're talking about the top. But if I look at the assumption, I would say it's a set. So there's nothing. It's just,
if it is a set, but
so you're
yeah,
from a sequence to a set.
Yeah, but in the categorical representation, how do you say it's a set? Again, you have to have some kind of closure on the permutation. You have to spell that out somehow, and because obviously it is a set. But it's a weird combination of things being strict and non-strict at the same time. Because if you have a lambda calculus without, I mean, I haven't seen it done, but maybe it's doable. Like if you have a lambda calculus without product, maybe you can somehow say that you can say your tensor is strict, maybe, and then this would work out in a simpler way. But if you make your tensor strict, then you can't do products because products require non-strict. So now with this interpretation into diagrams here, the actual direct representation that you would get is something like that, with a lot of copying and discarding of variables as used in the environments, and because they're pushed inductively, these environments, and then whenever a variable is not used, is discarded. But because of the coherencies of the Cartesian product, this can be always simplified to something that ends up looking in the way that you would like it to use, without redundant variables hanging. And all this again is done without, it's not like a picture illustrating a concept, it is a representation, formal representation of the context. And here again, there's some, I'm not going to go through it, but you can prove all the equational rules of the lambda theory in this model in a very nice, formal, diagrammatic way. But these are diagrams. These are, at some sense, we are still bound by intuitions. Like all these things are in the same realm of rigorous yet informal, where two-dimensional matrices do. If we want to make them formal to the point where we actually implement things, this is not going to be enough. What we need to do is to implement it as a combinatorial structure. And this is something that we call hierarchical hypergraphs. That's quite a mouthful. My former PhD student, Moroya, calls them hypernets. And I think that's a reasonable name to call them. These definitions are, I'm not going to go through them, but I'm just going to say, look, they are formal. So we're talking, we don't need, at this stage, we don't need to look at the pictures in. These are just mathematical objects. And now here, these pictures are really just used to illustrate the concept. But these are things that you can actually implement in some programming language. And moreover, you can show that DPO rewriting theory works on top of these hierarchical hypergraphs. So these equations that involve graph transformations. Yeah, it took me 45 minutes to say graph transformation, but they involve graph. They can be specified as graph transformation, and then we can extract all these details. And because this is DPO rewriting, it is going to work. Now, when you do DPO rewriting on graphs which are representations of string diagrams, the rewriting has to be modulo the equations of the string diagram. You don't want to do a rewrite. So basically, if you have two representation of the same thing and you apply the same rewrite, you want to get two representations of the same thing. You don't want to create. And that is technically a bit tricky. Luckily, that's where really the contribution of Fabio was essential, because Fabio and along with a lot of his collaborators like Paolo Sobocinski and Fabio Gaducci are world experts in these rewriting modulo theories. We could kind of put all this together and have a nice draft rewriting theory. But once you do it, this is something that you use for implementation, but it's again in informal yet rigorous reasoning. It's not really what you want to do. But you can use it to implement things like operational semantics of programming languages based directly on graph transformation. More precisely, strategic graph transformation, because when you evaluate the term, you evaluate the term relative to a strategy. You only find certain redexes and you apply transformation at those redexes. That gives you, if out of the lambda calculus, you get call by value lambda calculus, call by name, call by need, and so on. It's not about the rewrite rules, because the rewrite is always the same, it's just the Ghica rule, but the schedule, how you search the graph for this transformation. And this is actually, I find it both intuitively appealing, but also technically it's a very powerful thing, because it gives you a much better account of the intentional properties of a particular reduction compared to term-based analysis. Because you can model sharing in a way that you can't really do it very well in the term-based. So a lot of Coco's thesis was about analyzing the complexity of call by value and call by name based on this graph transformation understanding of syntax, which is very elegant and very productive, I think. And it can be extended with arbitrary rules. So here I'm just showing you some like a crazy rule. Call CC is probably one of the craziest operation that you will find in programming language. Is actually implemented and running. It's a way of saving the current continuation and using it later. So it gives you an extremely powerful control operator. And the semantics of it can be represented as a graph transformation quite easily. In some sense, maybe even more clearly than with a term-based operational semantics. Where in a term-based operational semantics, when you give a semantics of control operator, you really have to keep track of the context, how it interacts with the context. In a graph-based semantics, quite nicely, you can do that as a local transformation, which is, I find, again, quite surprising and quite neat. I shouldn't say that all operations can be given as local transformations. Some operations are a bit more complicated than that, but all of them can be given as graph transformation, usually, which tells us that these are really good intermediate representations for compilers. And indeed, the kind of compilers that we work on, which are compilers for mainstream programming languages, and they are industrial strength. They are used, or they're going to be used in an industrial setting, and they are based on intermediate representations arising precisely out of this methodology. So now, before I conclude, just give you a quick, some quick interesting application. One is type inference. I think type inference is one of those subjects that if you want to enter to the area as a student, it can be quite complicated. And the reason why type inference is complicated is because the rules, like if you look at any tutorial formulation, the Hindley-Milner type inference, like the core type inference algorithm that programming language use, it's very difficult to understand what is going on. Like, how did this person come up with this algorithm? It's just baffling. But if you look at it on a graph perspective, it's quite obvious what's going on. It's an exercise in labeling. Every constant in your language is going to have a type. And if you have polymorphic operations, such as function application, the type is going to include variables. But if I go from this side of the graph or from this side of the graph, I'm going to get two different labels. So now I'm in a graph, so the labels have to coincide. And just by going through all the labels, just going through all the wires in your graph and collecting what has to be equal to what, that gives you the unification system that you need to solve in order to type check your program. And I like this because it separates the conceptual problem that you're trying to do from the algorithmics and the heuristics of actually solving that problem efficiently. Because once you have a system of equations that you need of unification equations, obviously to be efficient, you don't want to solve all of them. In a turn, you don't want to resolve every intermediate type. Only when there is a problem, find what the problem is, and in some tips, point at the interface. So looking at it as a labeling problem on a graph, I would say that it mystifies a lot of type inference, and it just separates the conceptual part from the algorithmic and heuristic part of making it efficient. Another thing that is quite mystifying for people when they start looking at programming languages, closure conversion. Closure conversion, and it's like closure conversion and monads are the two things that you can find a million blog posts explaining each in its own flavor what is going on. So that tells you that there is a need for one more to explain it properly this time. And this kind of explanation can be helped by the graph perspective, because what we want to do in closure conversion is to make our programs more like C. We want to make our program as a list of functions in global scope that are possibly mutually recursive, but they're all in global scope. We don't want to have functions inside functions, because at compile time or at runtime, we don't want to generate new, at runtime, we don't want to generate new code, depending on the environment of that inner function. So we want to yank them out. So if you have this kind of general shape of a thunk, if you have some inner functions here, it's very easy to pull them out because this is actually one of the substitution laws of the lambda calculus. This is like lambda lifting. But you cannot do lambda lifting if your thunk is here behind some other bindings. I cannot just take it out. Or if I do take it out, I have to introduce some extra code so that this is used inside the original term in the same way that it was intended. And the whole like if you want to take a diagrammatic or graph-based approach to closure conversion, the problem is, how do I synthesize these two adapters? And there's not a unique way of doing it. There's not like one closure conversion. There's all sorts of closure conversion, but for pedagogical purposes, you can quite easily come up with something like this, and where basically some of the arguments of the function, some of the bound variable of the function that Yang tells become explicit arguments, and then you also have to propagate the extra argument for those arguments, and that gives you the closure conversion. I mean, it's not, by no means, it doesn't trivialize the subject at all. It doesn't make it it doesn't make it easy, but it takes away unnecessary syntactic detail that can be quite baffling. And probably the one place where syntactic detail is the most baffling is in a classic paper by Perlmutter and Siskin called the Lambda, the Ultimate Backpropagator, which gives a working algorithm for reverse automatic differentiation. And from a practical perspective, just because I'm wrapping up, this was what convinced us of the power of the diagrammatic approach, because we tried to actually prove the correctness of these algorithms. So this is kind of some part of the term-based formulation of the algorithm, and it's got an insane amount of these kind of conventions on variables and dealing with variables. There's a lot of variables around. And nobody actually proved that it is a correct algorithm. It was widely implemented. It's very efficient. It's a great algorithm, but we managed to prove the correctness of it only recently, so 2023 CSL, using string diagrams. So the formulation of this algorithm, when you make it into string diagrams, what happens is that you can take a string diagrams and then you can slice it vertically. Whenever you have two things in parallel, you can just offload them a little bit like this. So if you want to prove something here by induction, it's just baffling because there's so many variables, there's so many complicated bindings. But here, you remember when I showed you that sliced representation, which computationally was very bad because it obscured all the redexes. Here, we don't care about redexes. We want to prove something. And now we can take a term, and if we put it in this kind of sliced format, then you can actually prove the correctness, just making an induction on a list of components, because all these components are in an ambient environment where the rest of the graph is just wires. So they're kind of irrelevant. So we can prove the correctness just by making an induction on the list, and I think that's very nice. One of the authors, Perlmutter, I corresponded with him because I tweeted about this, and somebody helpfully forwarded to Perlmutter, like, look at what this guy is saying about your work. But he agreed. Like that's why they couldn't prove. It's just too complicated. Here, like, look, they even have like dot dot dot. Like try to do induction on a formula that includes dot dot dot. It's not easy.
You also have dot, dot, dot. You also have the variables.
Yes.
So
But
if you explain.
in the paper we don't have the dot.
Okay.
Yeah. So again, you can always use these things for illustration, or you can use them for and actually this is not in the tutorial that it's on archive, but for this one, for the details, you have to look at the original paper, because we do basically. So the idea is like this: you can take the diagram, you can manipulate it graphically, so that it has this particular shape, which is usually called sequential foliation. And then you extract the formula for it, which is just a long composition of things. And you do the induction on the formula, you don't use the diagram. But here, so we do have something more formal than this, but in the original paper, that's as formal as it is. Thanks for pointing that out. So to conclude, all these things that I said make good syntax. They become all these terms that we worried about at the beginning. They become the same graph if we use a diagrammatic representation. So that makes, in my opinion, and according to some criteria that I set out earlier, that makes diagrammatic and graph-based representation of syntax great. Thank you.
Very nice talk. We have a little bit of time for questions. Yes.
Well, I was wondering, it was very nice to see this, but your mission is to, or at least in the string representation, absorb these movements so that, well, using modulo isomorphism, but essentially you are replacing inequality modulo differences by isomorphism of your diagrams.
Yeah.
Now, isomorphism is itself a very hard problem. So if you look at it from that perspective, you can actually gain something.
Yeah, you do gain a lot. I think that's an excellent, because if you want to come up with let's say some kind of pathological testing example in which the diagrammatic and the graphical syntax do not bind anything, that's very, very possible. I mean, sometimes the complexity of the problem is of the problem, and just by changing the representation, it's not going to help. You're just pushing things around. So now what happened is that in certain situations, and in the particular, maybe it's because of the shape that these graphs have when we represent syntax, they do turn out to simplify the algorithmics a lot. So it doesn't simplify it in the way that some kind of asymptotic complexity, but in terms of like a heuristic, right? So if you use a heuristic, if your heuristic is well chosen, and for that application domain is going to improve things a lot, but you can always come up with, I mean, probably the most trite example is like the Hindley-Milner algorithm, exponential. We use it because for the shape of programs that we usually do, it doesn't, this exponential blow up is not triggered. And I think that's kind of similar with these diagrams. They just work for this. They are an efficient representation for the kind of graphs that arise out of syntax, which are, I mean, they're quite special. I mean, they're not arbitrary. They are quite special.
The characterization of those graphs.
No. Yeah, I mean, I don't know what it means to have a characterization of syntax. With another PhD student that finished recently worked on things that are more that require more global transformations. And also I would say that once you understand the graph representation, it can actually improve your understanding of the linear syntax. So for example, if you have if you look at the graph representation from the lambda calculus, you need to have a baked-in representation of substitution, because the sequential connection of two terms is substitution. It's like it's a lead binding, but the lead binding that's not desugared into lambda as well. It's a special.
So did you try? So I saw lambda calculus in fashion. Is there probably also worked on bigraphs and calculus? And semantics.
Yeah.
So do you have any experience with?
Exactly. Yeah. Also, Detlef has worked on hierarchical graphs.
And bigraphs themselves.
Yeah, we looked at a lot of them. I don't think that there is if there was, I mean, we would have loved to be able to use something off the shelf, but to do the kind of rewrite that we wanted to do, this kind of DPO rewriting on the hierarchical hypergraph, and also the particular limitations, like for example, the hierarchical hypergraph that are needed for syntax are in some sense quite simple compared to the full power of hierarchical hypergraph, because they are completely hierarchical. And you don't have any kind of links.
That take the platform. You have what's called scope extrusion.
Yeah, exactly. Yeah, I don't.
Can you capture that?
I don't think so. We didn't look at the power calculus. No. I think this is. But I mean that's why bigraphs were invented. Probably they would work better, I presume. But to giving this kind of structure that lambda introduces, you can work with a simpler notion of hypergraph. So our notion of hypergraph is much simpler than the ones that we found in the literature. And again, for the domain, we wanted something as simple as possible so that it makes things easier, especially for these writing modulo theories and for doing DPO rewriting. It was actually, I would say, a lot of fiddly work to come up with the right, because when you draw the diagram, you can envision so many ways in which you can spell it out as a combinatorial logic. And then you go through all these proofs, and some of them don't turn out not to hold. So yeah, it's a fiddly and challenging task, I think, to come up with this precise representation that satisfied the properties that we wanted.
Connection between string dividing and general dividing. And you explain the transition from string to string dividing, you end up in graph body.
Yeah.
You said before string dividing is algorithmically solved or something.
Yeah.
But which is the same true graph dividing model. Dividing model is always solved, I would say.
Okay.
So what do you see are the relative advantages, disadvantages? What is that really set of advantages?
I don't. To be honest, I don't have a very strong. I mean, I have some kind of personal feelings of that some things go well, because some of them, for example, the reverse automatic differentiation, we do implement it. We did prove it correct, and I know that how important the role of string diagrams have been. The graph rewriting stuff, we haven't worked with it in practice. So in fact, when we do specify these optimizations as graph transformation, but we don't extract the code automatically, we just give it to a developer. That whenever you see a diagram of this shape in the program, replace it with a graph of this shape, and then people do ad hoc rewriting on the data structure. We haven't implemented as graph rewriting. I think, maybe it reflects maybe it reflects a little bit of the fact that it would be a lot of work, and I don't know how. I don't have a good feeling, but I think it would be a good for a collaboration project or for kind of some academic exercise. I think it would be interesting just to see how well it works, because also the language that we have is it's a general purpose language that it's very complicated. It has dark corners, it has object-oriented stuff and dynamic dispatch, and all this is like a string diagram for all of that. But to do the graph rewriting for all of that is a bit. It seems to be. I mean, if you give a programmer the specification of a transformation as change this to this, it's quite easy. They can do it. So it's a bit demotivating now to go to build a super complicated tool that we don't really know if it's going to work good. So yeah, I don't have strong feelings.
Okay, maybe just one last question and then we continue over coffee.
Fabio. Oh.
I can read it, yeah.
You can see it. Okay.
Do you think it is possible for the closed case to discuss also about property of rewrites, example concurrency? Just reading.
Yeah, I think so. I think we do have some preliminary case that is encouraging. I mean, there's nothing published, I have nothing to point to it, but just kind of from preliminary studies and exercises, I haven't seen any potential like big pitfalls. I think it can perhaps be accommodated by the existing framework, and I think that can be done. Yes.
Okay, maybe we go to the coffee break.
I can speak.
Okay.
Just take a question, but I can ask
Okay, let's give another round now. We are back here at 11.